Angles as a concept come naturally to pretty much everyone. If you take two lines and you intersect them, then they will create an angle, and we denote this angle with the Greek letter theta. Now this angle is a measure of how fast these two lines will separate. So for an angle of 0, the two lines will lay on top of each other and will never separate, and they are in fact parallel. For smaller angles, the rate at which the separation increases is smaller, and for bigger angles it's bigger. And if you keep increasing the angle, then you will reach a point where the two lines make a perfect cross. This is known as perpendicular angles or a right angle, and it's usually written with a little square. And this, in a sense, is the maximum point for the angle, because if you start increasing the angle again, let's say like this, the rate of separation will actually decrease instead of increase until the lines are on top of each other again. But they're not exactly parallel anymore, they're anti-parallel. Because let's say our initial line started here and pointed that way, and then we took another line that was directly on top of each other and then rotated to that point, it would point in the opposite direction. This is what we call anti-parallel, and these lines correspond to an angle of half a revolution. Now, if we continued increasing the angle, we could see that this second line would come down here, and it would again be parallel, but kind of in the opposite direction, because this would be parallel like this. And then if we continued this, we should realize that the two lines will again coincide again. They will be parallel, and at this point we have completed one revolution. And so this angle is effectively the same as our angle of 0. And then if we started to increase our angle again, all the other angles we get would be effectively the same as the angles that we had before. They would just have one revolution added onto them. So it seems that we could quantify our measure of angles by referencing the revolution, because once we go past the revolution, we can describe any other angle as a certain angle plus however many revolutions. So we want to describe our angles as proportions of a revolution. We already described the anti-parallel angle as half a revolution, and our perpendicular angle here would be a fourth of a revolution, and the second perpendicular angle here would have been 3/4 of a revolution. And so this proportion I'm going to denote with a little lowercase n. And so n is just like 1/2, 3/4. And so we're going to use this to define our angle. But we need to reference it to some value. That value would be a revolution, but we need a specific value of that revolution. So the choice that we use to represent a full revolution could be kind of arbitrary. One commonly used convention is to use 360 degrees to represent a full revolution, and then the angle is whatever proportion of that 360 degrees that angle is, and this is known as degrees. So we can see that the angle described by this convention of a half a revolution would be 180 degrees, and the revolution described by a fourth of a revolution would be 90 degrees, and so on. But this may not be so satisfying of a measure of angle because it's kind of arbitrary. The value of 360 degrees pretty much just comes up because it's easy to divide 360 by 4, 8, whatever. So we're going to want a less arbitrary way of measuring our angles. One thing we can do is we can take our concept of intersecting lines and we can put them in a circle, like so. Now we can see that the proportion n that we've described before would now be the proportion of the circumference that our two lines would bisect. So for, let's say, half an angle where the two lines would make another whole straight line, then the proportion of the circumference that we've bisected with these two lines would be half of the circumference. So this proportion of our circumference is known as a sector, and maybe we can use this sector to define our angle in a less arbitrary way. So, because there's a direct correlation between what angle we have and the proportion of the whole revolution and what sector we have and the proportion of the whole circumference. So the question arises, what circle should we use as our basis then? Well, a quite natural choice might be the unit circle. We use the unit circle to define our sine, cosine functions, and so maybe it should also be used to define our angles. And so the unit circle is simply a circle with a radius of 1. So this angle is going to be whatever sector the angle bisects from the unit circle. And so we're going to define it as our proportion. Again, it's going to be the same proportion of whatever the full circumference of the unit circle would be. Now, the circumference of any circle would be 2 pi times the radius of the circle. And since our radius here is 1, it's going to be 2 pi. Now, this way of measuring angles is known as radians, and I will be denoting the angle in terms of radians with a capital R as its subscript. Now, the name radian comes from the fact that to get from an angle in terms of radians into sector length, all you have to do is multiply by the radius. Now, this direct relationship shouldn't be so much of a surprise since our definition of the radian is so intertwined with the sector of a circle. Now, to see exactly where this relationship comes from, you have to understand that all circles are similar. So, if you have a circle with a certain circumference, let's say circumference C, and you scale it by some factor k, then it will create some new circumference. But if for that new circle, its radius, its new radius, radius prime, would also be that same scalar times the original radius, all parts of the circle gets multiplied by the same constant. Now let's consider our unit circle. If we scaled our unit circle's radius by some constant k, then we're going to get a new radius. Let's call it radius r. But because our radius of the unit circle is just 1, we can ignore it, and we realize that our constant would be equal to whatever our new radius would be. So our radius of our new circle will be this constant, the scaling constant. So if we considered some other part of the circle, let's say our sector would be the scaling constant times our unit sector, the sector that would be in the unit circle, and we can make some substitutions. The k is our r of our new circle, and then our unit sector, well, that would just again be the proportion of the circumference, or n2 pi, or because our n2 pi is our theta angle in radians, our sector length is just the radius times our angle in terms of radians. Now, when dealing with degrees and radians, we may want a way to convert from degrees to radians because we're pretty used to using degrees. Now, this isn't too hard. We know that our proportion n here is going to be the same for both angles. It's how we define the angles. And so we can just set these two ends equal to each other. But first we should divide both sides by their respective term multiplied by n. And we get these expressions. And then we can set these two expressions equal to each other and then multiply the 2 pi over, and we get that pi over 180 times our angle in terms of degrees is going to give us our angle in terms of radians. The pi over 180 is, in a sense, the conversion factor to get from our degrees into radians.